record the session. There we go. Good. Okay, so last time we were implementing the traveling salesman greedy algorithm. So just to, where was it? Notes. Okay, there we go. Yeah, so just as a refresher, last time we were implementing this greedy approach, which you can see abstractly depicted here, just like possible different configurations of your system, the thing that you're trying to optimize. Imagine that this is really, really huge, and therefore you cannot just go through each of them. And therefore we resort to this not very good, non-specialized, but quite general and easy, relatively easy approach of just having one configuration that we are looking at some moment, and then trying to change it a little bit randomly, and then just after the random change, looking for its cost, and if it went down, we just accept that and take that modified configuration as the new one. Otherwise, we could reject the proposal and just look for something else until basically we end up in a situation in which we are trapped in a local minimum. And yeah, so, and in our, so this, which is depicted here graphically, is described like this, a little more precisely. Pick an initial guess, and then for a given number of time steps, well, assuming that's sufficiently large, just pick a neighboring configuration somehow, and then check the cost difference. And depending on, and you either accept the move here or reject the move, depending on whether the cost is smaller or larger, or smaller or equal on a side, or larger in the other. Okay, so this, and we were applying this to the problem of, not this one here, finding the traveling salesman problem. So this is just an example of one configuration that connects, I think, all major cities in the US or something. It's very complicated, as you can see. When the number of cities is large, it's not an easy task at all. There are lots and lots of combinations of actually permutations, sorry, of the cities, and each permutation of the city, more or less, apart from some redundancy in the representation, each permutation of the cities can represent one possible route. Okay, so we're saying that, and we went on and started implementing it. Now, I have uploaded already the code from last time, a couple of versions of the code, the sketch and version 0. I've also changed it in case you hadn't noticed. But very tiny changes. I just wrote here, I had written a compute delta cost function that we are going to implement later. Instead of just directly comparing the costs, I have a function for that. And the rest is, well, basically the same, but I added comments. So here, explaining what we are doing. So this is the same code as before, essentially, with very, very minor, tiny modifications. Okay, and we were in the middle of this, which was possibly the part which is harder to grasp, or one of the subtle points of this code. So this is exemplified here. We were trying to implement one way, which is just one possible choice of modifying the current configuration into a new one. So as we said, the general scheme is I have some current proposal and I want to change it a little bit to see if I can do better. And the way in which you decide to propose these little changes to the current configuration can vary. I mean, it's to some extent arbitrary, and we chose one which I just told you that it kind of works well, okay, relatively well. And the choice is to swap two edges. And so now when you go from the description to the actual implementation, you have to make all sorts of decisions, how to represent the route internally, how to represent the cities, the coordinates, how to represent, and how to perform this switch of paths, this swap of paths, sorry, in an efficient way. And by the way, I think I might also, so here I remind you, there's a tricky part, and I think that there were a couple of questions in the forum that I received. So I'll try to clarify very briefly something here again. So here we have two sets of indices, right? As you can see here, the blue ones and the green ones. Here, and those would be the blue ones here and the orange ones over here. Okay, so sorry for the confusion, but the orange ones here are the same as the green ones around here. That's what they mean. And the confusion comes from the fact that all these indices run, both these sets of indices run from 0 to the number of cities minus 1. So from, in this case, from 0 to 6. But they have different meanings, okay? So the root ones, these root indices, 0, 1, 2, 3, 4, 5, 6, that we see here, or that you see in orange here, these represent how far along we are in the route, okay? Whereas, if you look inside the route, so not the route indices, but the route contents, you see them, for example, here on the left, and the route contents represent city indices. So the index of a city, which you can think of, if you want to, as basically its name. So you can think of, say, for example, I don't know, city number 3 as being Tokyo, whatever. City number 2, New York, if you want to give it a name, okay? But in our case, the names are just really integers. So here, when you see a route like that, you can read the index as the start of the route, then the next step, and so on. But if you look at the contents, then you would read the first city in the route, which is also the last one, and then the next city in the route, the next city in the route, and so on. Okay? So now when we want to propose this move, we need to pick an edge, not just a city. So we need to pick, say, one city along the route and the one that follows it. Now, in order to do that, we need the index along the route, not the name of the city, because if you just give you the name of the city, say New York, you don't know what comes next. But if they tell you the city, the index in the route number 3, you can look at what the content of route at position 3, which is 0 in this case, and also at position 4, which is the next one. So you have this information about which two cities are connected, okay? And so you have the edge that connects them. So here in this example, if I extract, and so we are using, just to avoid confusion, hopefully, we're using E to denote the indices of the route. So these ones here, or the green ones, if you want. And so you pick two numbers like E1 and E2, and these represent this edge here and this edge over here. So the one starts at index 1 here and one at index 4. Okay? So I hope this clarifies things. And then when you swap two indices and you reroute things, so in the rerouting, I mean, the starting point is still here, okay, in this case. Then you keep going as you were going before, but then you make a deviation. Then at the bottom of the picture, you go back, but along the same path that you were going before, you reach this point number 2 here, or 6. You go to the other side and go back to the beginning, okay? So here we have transformed this route into, well, with the direction starting here and the direction like that, into this route here. Okay. Right? So far so good? More or less? Yes. In code, now you just do this analysis on a sketch on a piece of paper with a small example, try to make the example bigger, trying to see the different options, whether it generalizes or not. You try to figure out, to understand what's going on from the picture and what, I mean, you look at, decide what should go on at the level of the picture, and then you translate that in what should happen to the internal representation that you have in the program. And so we are going to translate this idea, this scheme, we translated that into an operation on the internal array, which, if you look at it, just consists in taking a chunk of the array and reversing it upside down, which in code is written like that. And so you see there's a forward direction here from E1 plus 1 to E2 plus 2. This is a chunk of the root. And here we have basically the same chunk of the root, but indexed in the opposite direction. And the reason why it doesn't really look as being the exact same chunk is because here we have this +1 and +1, and here we don't. And the reason for that is just this convention in Python that the starting point is included and the last one is excluded. So if you go in the forward direction, you include the first part, but you need to, so the first one is E1 plus 1, and you need to go beyond, just one step beyond the end. But if you index in reverse, you start at the end and you go one step beyond the start. So there's this +1, which is on one side and not on the other, okay? Because of the -1 here. Good? Okay, a little bit tricky, but if you just do tests on the console with small examples, so for example, if you just write down this root and try to put E1 and E2 equal 1, 4, and you try to apply an operation like this on this example, and you check whether this other example actually comes out or not. So you should do things like those when you're writing this code. Okay, so I mean, just do something like P, and then you say an example root could be an array. I can write the example 32600154. Well, with commas possibly. Something like this. And then I can do E1, E2 equal 1, 4, which is these two. And then I can try to do R of E1 plus 1, E2 plus 1 equal R of E2, sorry, E2 E1 minus 1, which is this line that you see here. And now see what happens. 3210654, 3210654, which is what we were expecting. Okay, so this is kind of how you do it. You do a little example on paper, check with a graph, check that everything works, then write your code, then check that your code works in a few examples, and now we are pretty sure that this line is doing what we intend it to do. And if you apply this again in principle, it should work. It should twist the thing back in position, right? So you may try that. So this is another check that you can perform. You can do this, and and well, it did. You see, it reverted back to the original one. Things like that. Okay. Okay, but what if? So this is where we were at. Now, so let's revise what we did before that. Well, this is just reading out the length of the root, and then we were extracting two edges at random, and then creating a new root, because this function, you see, You look at this function, it's used here, and the way it's used in this code, we are trying to fix this to do here, the way it's used in this code is that it takes one configuration and gives you a new one, and then computes the delta cost and possibly makes the new one be the current configuration if it's good. So we need to return a new configuration, and this operation here, as you've just seen, operates in place. So meaning it changes the content of the array, so it destroys the current configuration, it overrides the current configuration with the new one. So right now we are doing this copy and just creating a new root, which is the same as before, and then we change it. Okay. Okay. This has some problems which were mentioned last time. So this is only correct in a few cases. One could try. Well, maybe, you know, we can even take our R here, run the code, load the code. Now I have loaded the code, and they do propose move of R, and see what happens. Now, if you do this, you get back another configuration. You look at the previous configuration, and well, what happened? Nothing. Now, why is this? You try again. Well, this time something did happen, right? So what's going on here? You try it again. It happened again, something. So compared to the previous one, something changed, the last two pieces. You try it again. Nothing changed. So it seems to be working sometimes and not others. Okay, so if you find a situation like that, what you need to do is, unless you immediately see what's going on, which some of you probably can, but maybe not all of you, if you are in a situation like this, and this is a very, very common occurrence that you write a piece of code, it seems to work on your examples, then you try it on more examples, and sometimes it doesn't do what it's supposed to do, right? So this requires some debugging possibly. And the easiest way to do that is just to print what's going on and see if anything comes up. So something like E1 equal E1, E2 equal E2, for example. This, I guess this would be sufficient. So let's try again. Now E1 is 0 and E2 is 0. Now look at this, for example, 326010, 3260, nothing happened. And now, why did nothing happen? Well, in this case, we extracted the same index twice. So this was mentioned last time, but as you can see, with a little bit of debugging, already you notice something not right here, clearly not right, okay? So we can start fixing that. Okay, so how do you fix that? Well, we are trying to take two integers at random, but the thing is, we have some conditions now we've just seen. For example, one easy condition is that we don't want them to be the same. So if they happen to come out the same, like in this case, what do we do? Proposals? Yes.
Maybe a while loop.
Sorry?
A while loop.
Yes, so a while loop is the suggestion. A while loop that does what? Yes, good. So for those at home, the proposal was the proposal was do a while loop in which essentially what you do. So the general idea is do a while loop. Okay, I'm not writing the condition right now, but the thing is that I should have a while loop in which I do extract these indices, but then I perform a check. And if the check fails, like for example, they come out the same, I just restart again from scratch. Okay, quite easy. So just, so how do you implement that idea?
Why don't we just limit the second one from the first one till the end?
That's
Swap them.
Yes. Okay, so yes, good, perfect. So there's an exercise about this proposal that I'll give you, and I want to actually have a look at it. I mean, to actually try and do exactly this, because it's a natural thing to. Oh, by the way, for those at home, the proposal is, why don't we just extract the first index and then the second index, we take it from E1 plus 1 to the end, essentially, okay? So I want you to look at it by your own, do experiments and so on, but the point is that that approach doesn't work. It doesn't work, well, it doesn't work in the same way as I want it to work, in that the first index, if you do it that way, the first index is going to be somewhere, let's say, in the middle, okay? And the second index is always going to be concentrated on the last part. And so this will create a distribution of proposals which is not uniform as this one here. It's not really extracting two positions at random. It's extracting one position at random, and then the other one is confined to the second part. Now, this seems vague and maybe non-convincing, and that's why I want you to just investigate with by your own with an exercise which supposedly guides you to doing just that. But the point is that that's a natural thing to think about, but that doesn't really work well. I mean, okay. Yes, there's something I should mention here. I have just added an additional requirement on what we were trying to do. The additional requirement is that our proposals, our modifications should be more or less uniform. Okay, so this proposal of your colleague, it works, it fulfills my previous request, but now I have an additional one, essentially. So I sneaked in an additional requirement that I want this proposal to be uniform along the route. I don't want to because otherwise I would just fiddle more with the last part of the route and not with the beginning one. And I want to just be able to explore randomly every change in the and uniformly every change along the route. Okay, so not only at the end but also the beginning.
We generate them at random, and we only if they're equal, we start over again, generate them.
Okay, yes, essentially. Exactly. So now essentially the check here. So if we want to avoid this case that we have, that they are equal, you want to say if E1, you check it in reverse. So the way you do it is put something which is an endless loop by default. But if you pass the checks, then you're good. Okay, you can break out. This is a very common pattern. You start with the idea that you can, in principle, go on forever, but then, yes?
I thought about this first, but it also counts as a passive as arguments in the proposal, like E1 equals 0, let's say E2 equals 0, and then start the while E1 equals E2 with this.
Oh yes, so the suggestion would be, yes, there's an alternative way to do it. The suggestion is start with something that doesn't sorry, E1, E2 equals 0, say, for example. So the proposal is have something that doesn't respect the checks. Then you say, while you don't respect the check, do this. And you don't need this break, okay? So yes, this is another way to write the same thing, essentially. It's good, but you know what? We'll see just right now that, well, in a while, I guess, that this here is kind of easier because this check is only one of the many checks of the possible checks that we might have. And in other situations, your checks might be more complicated. So it's easier to isolate them somewhere else, or maybe break them down in a few steps and then do an if all the checks pass, all at once, rather than putting everything after the while. Yes?
Can we avoid the while loop?
There are ways to avoid the while loop, but let's hear what's your proposal.
I'm thinking like setting n as an array, and as soon as we get E1, basically finding one of the elements of the array from n.
So yeah, the proposal here is write all the indices in an array and then pick one element there. And when you pick it, just somehow elide it. So throw it away and then pick another element and you're sure. So basically that would cut the array, put a hole in the array, right? And now putting a hole in an array is a kind of an inefficient operation because you need to take the second part of the array and attach it to the first one. which means copying element by element from the end to plug the hole. And also you would need to create an array every time just for that, and to modify it just for that. So yes, that would work. It would not be very efficient. There is indeed, for this particular case, a way to avoid doing the while loop. It's kind of similar idea, but not slightly more efficient. I'm not going to talk about it right now. I think I have it possibly in an exercise, and in any case, I will upload it, one way to do it. But my point here is this is a general method, okay? So in a particular situation like this one, you can think of all possible optimizations. But if you want to do something in general where you extract something randomly, uniformly, but with some conditions that need to apply, this is a general way to do it. Okay, so just keep going until the conditions are fulfilled, and then you can break out of the loop. This works well as long as the conditions are not so strict that you spend millions of cycles just trying to randomly hit a jackpot, in a sense. Okay, so in this case, of course, this is going to happen relatively rarely, just 1 times out of n, and therefore it's not a big deal. Okay, so now with this fix, we can try again. You can debug it again. So you see now here, for example, you see 3260.154, 3260.154, and lo and behold, it's still something's going wrong because it's still the same route as before. And however, we have our little debug statement here. Yes. Yeah. So I was just exemplified. I mean, I was pretending just that we didn't really speak about, just demonstrating that you find a bug, you plug that, you try testing again, and then you realize, oh, there was this case like here when E1 is larger than E2. That's also wrong. I want to also check for that. So you want to go something like this. If E1 less than E2, then you can break, okay? However, I'm not really satisfied with this because now this is a much more stringent condition. It will fail 1 times out of 2 normally. So, but there's a little trick, at least. I just told you that you can avoid over-specialization, but I'm going to specialize here, this for this situation. And this is just the following thing that you can do. If E1 happens to be larger than E2, then just swap them. Okay, so I extracted that randomly. If I happen to have extracted one in the wrong direction, just swap the roles. And now I can keep this check here. Okay, and so now this thing is never going to happen again. Okay, so you could go on. Now, you see, now this 2.6 did work. It did something. At least we can try and keep going and check whether it did something or not. Oh, look at here. What happened here? Again. So you see, things keep popping up that we weren't considering, but you just fix them one at a time. What's going on here? Again, no changes. Here we have 5 and 6. They are not equal. They're in the right order. What do we do? Well, what you do is go and try a little scheme. If you don't see it immediately, you just go and do something like this, 0, 1, 2, 3, 4, 5, 6, let's say. Okay, so these are just the root indices. Okay, so this is the original root. Something like this. And then we are saying we are trying to swap 5 and 6. Now 5 denotes, if you remember, this edge here. And 6 denotes this edge here. And we are saying try to swap them. And if you try and do that, it's basically, it's a limit case, it's an edge case in which is as if you were trying to take just this one node and twist it, which doesn't make any sense. It doesn't do anything. If you look at it in terms of the operation here is just, you see, when you have, say, 1 and 4, you have 3 nodes in the middle, and you look at what we were acting upon, and this is just reversing three nodes. If you have 1 node in the middle, you're reversing that, which is like doing nothing. Okay, so that's another case in which our move is not good. So what case is that? It's when E1 and E2 have distance 1. So you will need to add more check, another check here. E1 must be different from E2, and E1 plus 1 must be different from E2. Okay? Run again. We can now try and check. Again, this changed. Now this changed again. This changed. Changed. See. Okay. At some point, oh, good. What's going on here? I didn't load the code, I think. Sorry. Did I reload the code? No, I forgot. Okay, so this one changed. This, okay. So here, this one didn't change. What's going on here? We have 3, 2, oh, sorry. 3, 2, 6, 5, 1, or 4. And then we have the indices. There's something funny here. The indices 0, oops, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. And we're trying to swap 2 and 5, which means this one here and this one here. In principle, it should work. So from 2 to 5, it should be reverting this part here. And see, we should see 0, 1, 5 instead of 5, 1, 0. Okay. And oh, okay. I think I'm making a mess here. Ah, yes. Sorry. Okay, so I was getting confused in fact. Okay, so what I did so far was correct by chance, in a sense, in that I was looking at move proposal and checking whether they were changing, but I was not comparing to R, I was comparing to the previous version, but I should have always compared to the current R, which is this, with the one that comes out from proposed move, which is this one. And this one indeed did something. Okay, so sorry about that, but just by accident, all our previous investigations were correct. Just now, it turned out, it showed up that they weren't. Okay, see what happened. I was changing R and looking at the outcome of this and comparing this to the previous case, which instead of comparing it to the starting point. Anyway, so we can have a look to see whether something changes compared to this now, all the time. Now this happens, this also works. This also works. So it seems to be working. Now, is there any situation, you could go on, actually here, maybe we can put it on the side and declare that it seems to be working well enough. Okay, yes?
Why doesn't it go
when E2 is 6, it might go out of bound, you mean here? Well, because that's the end of the range, and the end of the range is always allowed to go one point back, because it's excluded, so it's always allowed to go one step beyond the end. Okay, good. Okay, so yes, okay. So okay, it seems to kind of work, at least from what we can tell. Now, you see there's still a mistake here. I'm just going to put some options here, just to make the number of iterations that thing go away. And didn't I have, sorry, last time I also had written this, right? Oh, sorry, okay, so I'll rewrite, I have accidentally overwritten it, but it's easy to put it back. Okay, and yeah. Okay, so having fixed this and having added that, now we have done this to do. We can move it. Good. Okay, so I think I can save the file and declare that this is version 1. Okay, so we did a bunch of work and we save it in a sense as version 1, and now I'm going to call it version 2. So save as v2. By the way, I've also changed a little bit the name of the files. Just it's greedy TSP because we're implementing both the greedy algorithm and the TSP problem at the same time right now. Okay, good. So what's next is the computation of the costs. Now this is basic geometry, so again, there are ways in which we can be smart about this, but to begin with, we are going just to have an implementation which is simple but solid, okay, in a sense. So, what do you need to do to compute the cost of a route? You need to start from the beginning, look at the first edge, compute the distance between those two cities, store it away, keep the second edge, add the new distance to the old one, and so on, right? Just in a cycle. So, in order to do that, we need to have a little function that computes the distance between two cities, okay? So, what we are going to do is write a function called dist that takes the cities and then takes a city index and two city indices and tells you, which is, again, it's like the names, and tells you what's the distance between those. So, how do you do that? You need the coordinates of the first city. So x1, y1 is something like cities. You know what? I'll use this usual trick that I use, that is to write xy equals cities.x, comma cities.y, just to make them shorter, and give them shorter names. And then I can use the coordinates of the first city. So x city1 and y of city1 is just x of city1 and y of city1. This is how we call them, right? X and y. Yes, there we go. It's in cities, the attributes x and y are the coordinates. They are two arrays, and then we extract those for the first city. And of course, we do the same for the second city. So just change 1 into 2. Good. And then the distance is just the Euclidean formula, which is return and p, the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay? Should be good. Then, I mean, you should, if you write this, you should, of course, test it. Then the cost. So the cost of a city, of a route. So given the cities and the route, give me the cost. as I said, this is just a matter of going along the route. We go along the route using route edges. So something like c equals 0, you initialize something at a counter at 0, and then you do for e, which is an edge, in range n. What's n? We don't have it here, as you can see from, well, there are lots of problems, but n is just cities.n, which is also the length of the route. So taking one edge at a time, you say d, for example, equal the distance in the cities. Between which cities? So city 1 is the one at the current index in the route, right? And then city 2 should be the one beyond after that. And so you can write something like this. And then c plus equal d. Well, that's really, I mean, you can do this. Okay, so something like this, right? Not really. Yeah, what about when you get to the end? So the problem is that's been just pointed out. Oh, sorry, there's a, is it okay if I just computed the cost and distance function in one? Okay. Okay, sorry, there is a question before. Would it be the same if we picked E1? Oh, so this is about the previous code. I should really keep an eye on these questions. And perform the while loop only at E2 until E1. No, that's the same, okay, so the question here is if I just pick E1 here before, I pick E1 in advance, so I put this outside, and then do the while loop over just this one, keep just extracting E2. That would likely be fine in this case, but then this here would be a problem, I guess. Maybe not. I mean, probably it's going to be fine, this proposal that we have here, to just, for this particular case. But again, this situation here is more general. Yeah, probably that would be fine. It's not entirely trivial to see it, actually, because there are subtleties. When you extract numbers at random and you are aiming for a uniform distribution with a continuum, with constraints, it's, yes.
If you have the E1 that is the last in the series.
I'm sorry?
Like if you do like this,
Yes.
you would have you could get E1 that is the last number in the series.
The last numbers, and then there would be no possible E2, and I get in an endless loop. Yes, right, but then you would just do this anyway, and that would make the E1 that you have extracted and you're keeping apart you're keeping on the side, it would change role with another one, and then so in the next you will reject the move, and then maybe in the next loop the E1 that you have extracted at the start has become the one that you have extracted the previous loop. So you see why I'm saying it's not exactly trivial to understand whether this works correctly or not, this proposal. But I think it should. I think it should be fine. But this scheme that I wrote here is, let's say, easier to analyze in general. Is it okay if you just computed the cost and distance function in one? Well, yes. But it's okay, of course. You mean you can write all of this code here, essentially. But, well, it's just more cluttered. So that's just a little bit of separation of code, nothing more than that. Like if I build the vector that dist returns, plus I come back and just return the sum of that array. So this is slightly different. So the idea there would be to just compute all the distances in one array and store them and then compute the sum at the end. Of course, that's the same result, but you're just wasting a little bit of space. Nothing. We will see later, hopefully, or either we will see them in class, or I will just upload it and you can have a look at it on your own, as for one way in which this cost computation can be greatly improved. Okay. But not right now. Right now, we just write something that hopefully works. Okay, so this that I just wrote should hopefully work. Now we can use it. For example, when we display the cities, you can also print the initial cost. And that's... So let me write this. Cost of cities, and the root is x. Is there a problem in the code? Ah, yes. Ah, sorry. Sorry. I was jumping ahead. So, sorry. There was first this problem that was being pointed out before I read the messages. So the problem that was being pointed out is this one. And it's the fact that when e is the last index of the root, then e plus 1 is out of bounds. So you can check this, indeed. I mean, you know what? In this line that I was writing here, this would come out. Okay, so let's see it. Let's see it in action. I run the code, and then I say cities. I generate some cities like this, and then I try to call greedy on this problem, and of course, I get an out-of-bounds error. And where do I get it? Exactly in this line here, as we were predicting. Okay, so the problem there is that when E is the last city, the next city is not E plus 1, but it's 0. Right? So so we could add a special case for that. We could just do this and then say, so we could add something like this. This is one possibility. Sorry. So just go up to the end and then do something like this. This should work. Right? Yeah. Now, I have a little bit of a trick that I want to show you here, just because it comes up not just in this case, but in many, many cases in computer science. So in computer science, programming, it's surprisingly often that the modulus and remainder operations come out more often, Yes, so the modulus and remainder operations come out surprisingly more often than they appear in math. That's because when you, in computer science, it's all about discrete mathematics, essentially. And in discrete mathematics, operations with integers become more relevant, and the modulus operation in particular. So look at this. I'm claiming that this here, so let me go back here. Okay, so again, I have the range of all numbers, just like before. Now I'm claiming that this here fixes the problem. Why is that? Well, precisely because our root represents a cycle. And so when you have a bunch of numbers that you're going through and you want to explore them circularly, in a sense, you can just take the remainder with the size of the list or the array that you're going through. So in particular, in this case, when e is equal to n minus 1, e plus 1 is equal to n, and the remainder with n is 0. So this second line in that particular case is exactly as this, you see. And in general, when you're going through an array and you want to wrap around, you just use the modulus operator, this modulus or remainder, whatever you want to call it, this one here. This is called modular arithmetic, okay, in general. It's a very nice field of discrete mathematics as well. I think you know it well, but I just want to mention that it's surprisingly often that it comes up. Okay, good? Everything good? Okay, so this should work, hopefully. Cities. Okay, so now we are back on track because now what we need is to compute delta cost. We are almost there, right? We are almost there because we have the cost computation. We just need to define how to compute the delta cost, the difference between, well, the delta cost, it's between root 1 and root, or maybe, should I call them differently? Cities, root 1 and root 2, I guess, yes. Okay. So root 1 is the new one and root 2 is the old one, I guess. No, let's give them names. Root new and root old. Okay. So this is just the difference between the costs. So we can just write very, very naively the cost of the old version is just cost of cities root old. And then C new is cost cities root new. And then return the new minus the old. Okay, why do we want this, or do we want it the old minus the new? Well, let's think about it for a second. We want to accept when the delta is negative. The delta is negative when the new is smaller than the old, which is exactly what we want. Okay, so when the new is smaller than the old, we are doing good. Delta is negative, we're going to accept the move. Now, this to do here is done. There are no more warnings. Sorry, cities, greedy. Okay, well, still have to give the cities here. So I need to improve the sketch. By the way, we can also be a little bit more verbose. So when we accept the move, let's say that we print it, print f of new cost equal c, let's say. Now, what about c? C should be the new cost, so it could be the cost of x1, the new thing. And then when we are done, we can say print f final cost equal c. Now again, it could be c equal the cost of x here, because x is just what we are about to return. Okay? Yes?
Can we?
Yeah.
Cost,
Yes.
cost of x, not of x1. Isn't it if the first is x equal x1, then it's already updated, so we can compute their cost of x.
Here.
Yes.
Yes, exactly. See, yeah. So, yes, good. There's another thing that we are computing the cost from scratch all the time. Here, I mean, if we have just computed the delta cost and we know the old one, you can even say C plus equal delta C. You see what I did? I'm keeping the old one, the old cost around. And then since I've already computed the delta, when I accept the move, I apply that delta cost in a sense, and I remember the cost. And well, here, now I'm keeping track of the cost all the time, so I don't even need this. I mean, this should be, and however, we should have a check for that. So let's first thing see if this works. So cities, and then greedy. Oh, the first time that our code actually does something. Okay, works. Now let's see. It started from something. Now there's all sorts of proposals. You see that this was accepted because it reduced the cost. You see that after a while a new one was accepted. But there's some sort of funny thing going on here. Why? Oh, C to 0. No, C is being initialized here. You see, it's the cost of x, the current x. Okay, so let's see what happened. Well, something went. I mean, it's not bad. Okay, it's not bad. This is the display. This is what happened at the beginning. So this was the initial configuration. Now I haven't displayed the configuration at the end, but I can do it right now, I think. So let me keep this on top just to just to have it around. So if I write now, oh, I didn't save, but I can reproduce it. So let me run it again. Now, since I gave the seed, it should be reproducible. And of course, it isn't. No, it is. Good. Yes, so it's the same. It's the same. So now I have the root. Now I can do display of cities and the root. And let's see. Is it this one? No, it's some, I think it's some. I don't know. Well, it's this one. Did it change compared to the original one? Yes, did it? There's maybe it just changed and I didn't spot it. But in order to spot it better, let's do it this way. So first of all, we display it, and maybe, you know, just for the kick of it, we display it also when it changes. And however, if I do this, I'm afraid it might be too fast, but let's see. So I have again, oops, sorry, no, cities. And then I run this. Okay, it's too fast to be seen. Okay, so let's assume it changed, and then we will have a look at the picture in a while. But before that, I want to point out something, which is that here I had a cost, then a few moves were rejected. You see those. These were all proposals, but you don't see the new cost after those. At some point, we had this one. And then we have, this was accepted, and it was accepted, and it has the exact same cost as before. Isn't this weird? I mean, I changed something in a complete random cities. Supposedly, I have a new route now, but I look at the distance along the route, and it's exactly the same as before. It's suspicious, at the very least. Wouldn't you agree? I'm sorry? Sorry, can you speak up? I can't hear.
Maybe it's because of
the closing points.
Closing points, so we can't see the whole number after some decimal.
So yeah, floating point. Sorry. Is it about floating point approximation? Then, well, that's an hypothesis, but let me tell you, it's really, really, really unlikely. Okay. That you get something like this. I'm sorry, say again. Yeah. So yeah, that's the reason why the move was accepted. So that's not mystery. The mystery here is that there's some route, and then there's some other route which supposedly, I mean, something like what you have below there, a twist is supposed to have happened, and yet the cost didn't change. Yeah, it's a kind of what he was saying. Maybe they're just so close, and then you don't see it because of floating point approximation errors that the difference is in the, I don't know, 30th digit, but that's very, very unlikely. So can you spot something about this move here that was accepted? Yes? What are 0 and 9? They are the first and the last. Why is that a special case?
It does passes that U1 plus 1 is different from E2, but still it doesn't change anything because they have only one node between each other.
Exactly. So there's also something here. There's also something here that says, did you just invert the whole list? Which is, yes, another way to say this. So exactly one way or the other is a good way to put it. It's just that we have this check. So as you were saying, you look here, there's a check that we don't want to pick up a node, a position in the root, and then the one immediately following it, because we've just seen that doing that is just like twisting a single node, which doesn't do anything. But we forgot the case in which the last element of the root, I mean, we have picked the last edge and the edge number 0, which is indeed the one after the last. Okay, so this E1 plus 1, when E1 is equal to n minus 1, it's the last. E1 plus 1 is n. It's different than E2, but really they are the same because it's of this circularity. So we could either do this check in sense in a modular arithmetic or add a special case for that. Let me just save a file. I want to have a version that with just a bug fix, just because I want to put it in. So here we need a new condition. We need to check whether E1 is different from n minus 1, or, well, it's easier done this way. If not, E1 is equal to n minus 1, and E2 is equal to 0. The other way around, sorry. Is it this way? Yes, E1. So this is the situation. Yes. Okay. Confused? No? Yes? Good. Let's see if this fixes the problem. Sorry. There. You see? Now this, well, the moves have changed a little bit. Ah, yes. So you see, after this, previously, there was 0, 9, but now it's no longer there because it has been filtered out. And so you keep going with the other proposals, and eventually you hit something here. All right? And you get a cost of 5.5. Now, you look at the root, and it's not really good at all, apparently. So let's try to see if we can see something with bigger. So have a feel of what's going on with more cities. Let's see something like this. Okay, too fast, as I said. So let me just add a little bit of a pause in the display function, just so that we can see things happening. plt.pause 0.0001 something. Run this, run the cities. Okay, still too fast. I don't know. Maybe let me just try with a larger pause, something like this. Still too quick. So it gets stuck immediately, essentially. You see after, yes. Okay, sorry, I'm an idiot. I forgot one thing, that I just gave it 10 iterations. So it was, okay. Okay, let's go back. 0, 0, 1, and then, I mean, you could have warned me. Num iterations. Let's do 1,000 iterations. You know what? Let's go back to just 5 cities, 10 cities. Let's see if we can see what's going on. No, numiters. What did I call it? Numiters. There. Oh, you see. Finally. Did you see it? Did you miss it? Let's run it again. Finally, some reward for all our work. Okay, so it works. Okay, by the way, you know, in the new cost, here's what we could do. We could say, well, It's just let me do this. I now write iteration, well, t equal t, so just I know at what iteration the move was accepted. Here there was this debug statement that I'm going just to remove because I just forgot to do that earlier. Or was it? Was it? Here, there we go. The printing. Okay, run the code again. Just now we are done basically. Okay, it's just a little bit of polishing from now on. So create the cities and do the thing. Okay, so kind of interestingly, you might notice that after 63 iteration, this was when it found its local optimum, which in this case is pretty clearly also the global optimum. I mean, just by visual inspection, we can tell that it's the best thing you can do with this problem. But you can see that after 63 iteration, it did nothing useful anymore, and then the rest of the iterations were just wasted. But we don't care too much right now. Okay, and it gives you the array. Now, let's see. It's working, so are we done? Well, let's see. 100 cities there. And you see it's trying, and whenever you see a movement, it's some improvement. And it's improving, clearly. Now, we did not have enough iteration this time. How about that? So we need to be more patient because we have lots of cities, lots of cities. So let's say 10,000 iterations, perhaps, something like that. Can wait a little bit. You see now the time it takes. Don't be confused. The reason why it's so slow, it's just because of the posing. Okay, it's the display. Now, if you run it without the display, it will run faster. Now, look, this here is way better than it used to be. The cost is 9.36. Now, let me just remove this display, and you'll see how much faster it goes. Run it again. Cities, greedy, you see? Okay. Still, not great. Still, there are some positions. Look at here. If you look and can see here, for example, whenever you see some paths that are crossing in this problem, you know for sure that this cannot be the optimal solution. Because whenever you have two paths crossing, you could also always twist them and have something better by just connecting these 4 points like that. So we would need more iterations. I don't know, 30,000, 50,000, something like that. Okay. So now you see, now the cost has improved considerably. Now, after 20,000, now it's stuck there because it's just going through iterations without doing anything. See? It's just trying everything. It's clearly now it has reached a local minimum of some kind. There. And then you see, indeed, it's a local minimum because you can see it's a local minimum. It has no crossings, at least. It looks good. Is this optimal? Who knows? Okay, it's good. I mean, relatively good. It looks kind of reasonable. Okay, so there's no guarantee here that this is going to be the best that you can do ever. One thing that you could do is with the same problem, so the same cities, try and run it again with a different seed. So a different random run, a different initial condition, essentially, different proposals. See where you get. Okay, so you can say, okay, this was 8.11116. Now I can try instead of 100 and instead of this seed, I can change it. Even if I change it like this, it's going to be completely different. So I just run another one. 8.11 is the one to beat. Let's see, does it go down? No. maybe. You see also how it gets slower and slower, because the opportunities for improvement get fewer and fewer as you get a better and better configuration. So you see, look at this. This is also a reasonable solution with the same cities as before. Quite different, I guess. The solution here is 8.35, which we know now it's not the best because we had a better one previously. But if you looked at it, you probably wouldn't be able to tell that it's not the best possible one. Okay? So what we've just seen is that if you run the same thing over and over, you get slightly different results. They don't look, none of them, I mean, if you figure out how many iterations you sort of need and so on, you can see that you get things which look more or less similar, but they come out different all the time. So what's one easy way to, let's say, and also if you do one run, you get up to the end and then you're stuck there. Okay, so from here, we said this is a local minimum. Okay, so there's essentially no real way to take that and just tweak it a little bit. If you want to have a different configuration, you have to do some major changes, okay, to the root. So reroute big portions of the thing. Maybe instead, so for example, maybe instead of doing that, maybe from here, you could go down here and maybe come back here and then do the rest of the route, let's say from the outside or something like that. So big rerouting. So this means that we get, if you run it repeatedly, you get a series of candidates of local optima, hopefully, and then what you can do is just say we take the one which is best. Okay, so run the code repeatedly. All right, good. So for that, I'm going to create a new version. Let me close this, which is version 4, in which, now that we have a working code, so this is a working code, now we can start trying to improve it by just saying, for example, adding a number of repeats. Repeats. By default, I set it to 1, just to say no repeats. And then what I want to do is basically take all of this and do it over again, over and over again, okay? Something like that. So indeed, I start from here, and I can say, well, here I'm going to have 4 I don't know, in range repeats. Okay, something like this. Then every time I do this, I do all the iterations, I initialize the cost, and essentially I have all of this, all the previous code. Now, what I want to do, however, is every time I get here, let's say, have a best cost around. So initially, I initialize some best cost as infinite, np.inf, infinity, and best configuration, let's say, equal none. So at the beginning, there is none. I may say best x if you want. Okay, now init config and so on. And so at the end of each run, I can do if c is smaller than the best cost, then update the best cost equal c. Maybe for consistency, I should call it best c, I don't know, best c and best x, okay, just so that the variables are called the same name. Best c and best x equal x. Okay, and then here, instead of returning x, I return best x. And Okay, I'm not going to display everything. I'm going to display just the best one. So best cost, display cities best X, something like this. Okay? Not hard, a little bit of fiddling with just put everything in a loop, have something that remembers what's the best, and update it as needed. And then at the end, display that and return that. Clear? So I think I can run that. Let me give, okay, so repeats equal 3, for example. You can now do 3 repeats, let's say 120, and this would run, I mean, okay, ignore that. It's running, the first run, and, well, let's see what happens. You know, since I don't want to spend too much time with this, okay, let me try and stop it, good. Okay, I want to do a smaller sample, so 30 cities, for example, and then, I don't know, 10,000 or something. Okay, so this is first one, second one, third one. Okay, this is the best one out of 3. So it's already done. It found 5 for 24 was the best one, and it also happened to be the last one. No, it doesn't. It looks like it didn't work. 522, 524. Okay, there's something wrong here. The best cost should have been 522, I guess, or even 515. So there's some debugging to do. No, okay, there we go. See, typo. Okay, run it again. There. Okay, 1, 2, 3, and finally it says, okay, so it found 3 solutions, one with 524, 522, 515, and it just took the first one, which was the best one out of the 3. And of course, you might try to run it more, I mean longer. At some point, if you keep hitting several times the same configuration and it's the best that you can do, maybe at that point you can gain some confidence that that's just the best and there's nothing more to do. Okay, see what I mean? Okay, good. By the way, well, yes, this is good, I think. Okay, we're done with the code. I mean, it works. Now, what I want to do next is improve the way it's written and its performance. By the way it's written, I'm speaking about something called refactoring. As I told you at the very beginning of this journey about implementing this, my aim was to end up with a generic code, okay, for a greedy solver, which given any problem in a certain form can apply this this idea of optimization, and on one side, and the problems on the other. So you see here I have cities. Now, the first step for doing this kind of to do this kind of separation. So I want essentially to end up with different files entirely. one file where you have the optimizer, which lives by its own, and one side where you have the problem definition, which is also something. And then they should speak to each other. So the first step for doing that is something that came up actually last time, the proposal to make all of what we are doing here be methods of the class cities that we have. Now, this is sort of debatable, but what I want to do now, essentially, is to take this, which just represents the problem data. Cities now only contains the problem data, right? Now I want to take that and transform it into an object, which is capable of, which has methods for being optimized with a greedy solver. So I want to go essentially from a class cities to a class traveling salesman problem. Okay, city is just the data, but I want to have the methods here as well. So I'm going to create a new version, which is called v5, and it's going to be essentially the last step before we refactor it more heavily. Now I'm going to call this TSP. And just because this is going to be quite a big change, I'm also restarting the kernel right now, so clearing up everything so that I don't forget. So if you look at this, you see, sorry, come on, what's this? Go away, please. I want to remove this breakpoint. Oh, good. Okay, so here, this, for example, all of these can be essentially methods of the new class. So let's see, when you want to initialize a config. So the idea here is that the problem does not only the class does not only contain the data, the input data, the cities, but also the current configuration and other things related to the problem itself. So for example, I want to insert the root as a member, sorry, not, as a member of the class. Look at this. If I do root equal self.init config, and then here in init config cities, I turn it into this. And cities becomes self. Okay, so not root, but rather self.root, something like this could be. Or even I could do it this way, so remove that, but do it this way, self.root, and I don't even need to return it, actually. Because instead of returning from the function, I'm just storing it inside the object. So to make it even a little bit slightly better, I can do this and p zeros. So I initialize to something of length n, d type equal int, just to have the space. And then whenever I call init config, I can fill in its contents. Now this, having written this, it means change the contents of the root. So what I have here now is that TSP contains not only the positions of the cities, but also the current configuration, which I'm calling self.root, inside the object, and also this method here. So the object is always allocated. At the beginning is initialized. I could initialize it again if I wanted by just calling this method, and this method will overwrite the contents of the current configuration. Okay, understanding that what I just wrote there, self-root with that indexing expression, understanding the difference between that and this is kind of important. Okay, so go and look at the NumPy notes and do the exercises about NumPy if you're not clear about what this is doing. And if it's still unclear after some point, then you can just write on the forum. But just, I want to point out that this is syntax that you should know, okay? The same we can do with display. So again, it's just a little bit tedious. We can even, I mean, dispose, I don't know if we should comment it out. It's just substituting this with self, and that's it. The rest was already done. Propose move. Well, propose move. Oh, now this one is interesting. Propose move, look at this. It used to have root as, it used to have root as its argument. Now root is going to be inside the object. So when I make this a method of the object, I put self here. I don't need to give it the argument root because it's already inside, so I can just take it out from this. So look, I can say root equal self.root. And also here, n equals self.n. See what I did? So we're almost done. But this one here, the rest is automatic essentially, but this one here, listen about this. So here I had root copy and so on. I can propose the new root. Now this creates a problem. Okay, why it creates a problem? Because it creates a new root, and then because you want to keep the old root and the new proposals so that you can later compare them and then decide which one to keep. But now I'm keeping one directly in the object, and so where do I put the new one? If I put the new one in the object on top of the previous one, I'm overwriting it and I shouldn't. If I put it outside, it's not really, I mean, nice, let's say. That's a possibility. What we are going to do, because time is over now, I guess, right? So what we are going to do is to change this and split it in two parts. A proposal in which you just propose the indices. So it returns, essentially, return E1 and E2. Just return what you're proposing to do. Then the computation of the delta cost should take those two, compute the difference, and if you accept that, you should have something like this. Okay, so let me be slightly more explicit. Move equal E1, E2. So I'm encoding the move, and here I'm decoding the move, in a sense. Okay. And here you see, instead of when I accept, the root, the move, I don't need to work on a copy because now I'm actually really accepting it. And so I can just do this. Now what I did is just take the move. If I'm now accepting it, I just overwrite the thing, the contents. And the way this is going to work is that I propose a move. I don't. So this is going to be self.propose move. This is going to give me a move. And then I compute the delta cost of cities. Here I'm going to give it the move. And then accept the move is not going to be like this, but it's going to be like cities accept move of the move I've given. Something like this. Okay? We'll pick it up from here next time. But this is just a short anticipation of how we're going to reorganize things, making everything more efficient, cleaner, more separated, and so on. Okay? There was, thank you, Giovanni, for pointing out the mistake that I should really have a look. Uh,